Hello learners, my name is Amrish Singh. I am a research scholar in the Department of Mechanical Engineering here at IIT Guwahati. In today's session, I will be introducing to you a numerical modeling approach called as Discrete Element Method or DEM. This Discrete Element Method approach is used for the simulation of granular materials or the bulk materials. As we now already know that there are several additive manufacturing processes that use powder form of feedstock material. These additive manufacturing processes include binder-based additive manufacturing, powder feed-based additive manufacturing, and powder bed-based additive manufacturing. Thus, it becomes imperative that we understand the behavior of bulk materials. That means the behavior of granular materials. The fundamental understanding of granular materials can help us in designing efficient additive manufacturing machine tools. So this is the outline of my presentation. I will first start with a brief introduction to discrete element method. Then I will discuss some of its contact force models. These contact force models are essential for any discrete element method simulation. They form an essential part of the DEM simulation. Then we will be looking at material calibration. As you already know that there are several inputs which are required from the user end into the software. So how to extract these user inputs, how to extract the particle interaction properties, we will be looking at, briefly we'll be looking at those as well. And then I will switch to the DEM environment and we will be exploring some of its capabilities. So when it comes to the numerical modeling and computer simulations, I'm sure you must be familiar with CFD analysis and finite element analysis. The CFD analysis and finite element analysis assume a continuum. That means the media in question, whether it is a fluid or it is a solid, the finite element in CFD analysis assumes that the media in question is of continuum nature. That means if there is a fluid flow domain, we don't talk about the individual particle interaction between the water molecules within the fluid flow domain. We assume a continuum there. However, this cannot be applied when we are trying to simulate bulk matter behavior or granular materials. This is because the granular materials, most of the granular materials or most of the phenomena that relate to the granular material is affected by the individual particle interactions. Thus, this continuum approach cannot be assumed. In other words, in discrete element method, the overall picture or the macroscopic behavior of any system results from the microscopic interaction amongst the constituent powder particles. Thus, the continuum approach falls down in the case of granular media. So, discrete element method tries to resolve the constituent particles, resolve the interaction amongst the constituent particles. This type of a model is sometimes also referred to as Lagrangian model. Now, because we are trying to resolve the individual interaction amongst the powder particles, we can explore phenomena such as these. So the first thing that you see here is the phenomena of powder segregation. As you can see in this figure, at time is equal to 0, the bigger particles are at the bottom and the smaller particles are on the top. In the next frame, you can see that the smaller particles have filled the voids which are left out by the bigger particles. At time 4 seconds, we start to vibrate the system. So in this case, the vibration was at 16 Hz at an amplitude of 3 mm. We start to vibrate the system and slowly, as you can see, the powder particles segregate. That means the bigger particles come on the top and the smaller particles go to the bottom. So the problem of powder segregation can be solved or can be modeled using discrete element method. Another problem that we have seen before is in the context of vibration-assisted powder delivery nozzles for powder feed-based additive manufacturing. Here you can see that there is a delivery tube, and this delivery tube dispenses powder only when vibration is applied to it. So if we want to model such phenomena, it can only be done with the help of discrete element method, because discrete element method tries to resolve the individual interaction amongst the powder particles and thus giving you a microscopic or the macroscopic outlook. One other thing that we have already touched upon for the case of powder segregation is in the context of mixed powders for selective laser sintering. As you already know, that in mixed powders we have the structural powders or the structural material, and then we have the binder materials. So these two are two different powders. One is for the structural element, and the other is to bind these structural element together. If these two powder particles which are mixed together, if these two powder particles were to segregate in the recoating cycle, then you can imagine then it would lead to several manufacturing defects which we don't want. So we need to understand that how how the bulk material behaves with the surrounding equipment material and how it behaves amongst itself. So this is the generic approach of any discrete element method simulation. First, we initialize the problem. In this stage, we define what is the equipment geometry, what are the bulk material properties, what is the initial particle position, and so on. Having defined these elements or having defined these characteristics, the next thing we do is we determine what are the body and the surface forces along with the torques that act on the individual powder particles. Then we use the Newton's second law to determine each particle's acceleration. Then we can integrate that in time to arrive at particle's velocity and subsequently its position, the particle's position. So having arrived at these new particle positions, we mark these new particles. We mark these new particle states. Then a contact detection algorithm is run. If the contact is detected, we determine what are the contact forces using an appropriate contact force models. Then these contact forces in conjunction with the body and the surface forces are used to carry out the next iteration. Similarly, the simulation progresses until a user interrupts the simulation or the simulation reaches its completion. So as I previously mentioned, that contact force models are an important part of any discrete element method simulation. Here, I have categorized the particle interaction into two separate segments. One is called the contact forces and the other is called the non-contact forces. The contact forces can be further categorized into elastic and inelastic contacts. In the elastic contacts can be further categorized based on linear models. The elastic contact can be based on linear models, and the elastic contacts can be based on non-linear models. In linear models, the contact follows a linear relationship between the force and the displacement. Whereas in the nonlinear model, the contact forces and the displacement follow a nonlinear behavior, a nonlinear relationship. In this session, we will be exploring a contact force model which is called as the Hertz-Mindlin no-slip theory. This Hertz-Mindlin no-slip theory is used for the simulation of dry, non-cohesive granular media. But towards the end, we will also be looking at Hertz-Mindlin plus JKR model, the Johnson-Kendall-Roberts model, which is used for the simulation of cohesive medias. So cohesive medias are generally if the particle size is too small and the particles have some amount of moisture content in them, then we have to use the contact models that can model the cohesiveness amongst the powder particles. So a Hertz-Mindlin with JKR model can model the cohesiveness amongst the particles. Then there are several inelastic contact force models as well. These inelastic contact force models are typically used when there is a plastic deformation amongst the powder particles. So today we are not going to be exploring these inelastic models. Then there are several non-contact force models as well. So for example, if there is a van der Waals force amongst the powder particles, then we can use these non-contact force models. Also, if say for example the particles have charge on them, electrostatic charge on them, then through appropriate non-contact force models or the body forces, we can take into account these non-contact forces. Again, in today's session, we are not going to be looking at the non-contact forces. So the only body force that we will be considering would be gravity. So as I previously mentioned, that there are several user inputs which are required in the discrete element simulations, or with any simulation there are several user inputs which are required. Here I have categorized these user inputs into three segments. The first is material properties, second is geometric properties, and the third is interaction properties. We will be concerning ourselves with the Hertz-Mendelein no-slip theory, but towards the end we will also be briefly looking at Hertz-Mendelein JKR theory as well. So the material properties and geometric properties in discrete element method environment is quite easy to obtain. However, obtaining the interaction properties is a challenging task. So these interaction properties, depending upon what type of contact force models you use, can vary in number. So for example, in the Hertz-Mendelein no-slip theory, which accounts for rolling friction, needs these three interaction properties from the user end. These are coefficient of sliding friction, coefficient of rolling resistance, and coefficient of restitution. For the Hertz-Mendelein with Johnson-Kendall-Roberts theory, we also need an interfacial surface energy, because this JKR model takes into account the cohesiveness amongst the particles. So how to determine the coefficient of sliding friction, coefficient of rolling resistance, and coefficient of restitution for the granular materials? And remember, these properties have to be determined not just for the interaction of the granular media with the equipment material, but also amongst the granular media. Between two powder particles, what are the value of these parameters? We need to determine that as well. So what we can do is, we can go for an inverse approach. So in the inverse approach, what is usually done is, we first conduct some experiments and we look for a parameter that can characterize the experiment with a very easily measurable value. So for example, what we can do is, for the case of granular media at least, we can carry out an angle of repose test, a static angle of repose test, which you can see here. So this angle of repose test, what we do in this test is, we try to create a powder pile, and then we look at the angle of repose, the angle at which the powder pile sustains itself. So we look at this angle of repose. So the angle of repose is simply the angle between the flat surface and the conical pile. So the angle between the yellow and the red line, that will give us the angle of repose. This is easily measurable. We get the value from here. Now we go to the simulation environment. In the simulation environment, we try to set the parameters, even though the parameters are unknown, but still we try to set the parameters in such a way, through trial and error, such that the angle of repose as given by the simulation matches the angle of repose of the experiments. And then, and of course this requires an iterative simulation. With one set of parameters we try to do the simulation, then with the next set of parameters, and we keep on varying the parameters until the simulation results matches the experimental value. And the parameters at which the simulation results match the experimental values, those parameters would be the actual parameters for that material pair. Another very important consideration in DEM is the time step. So as I already mentioned, that discrete element method tries to resolve individual interaction amongst the powder particles. This is a highly time consuming task, and the computational load is too much. So what we generally try to do is, we try to reduce the computational load without too much compromising the accuracy of the simulation results. Here is one criteria which is used for the computation of time step. This is called as the Rayleigh time step. In the calculation of this time step, you will see that there is an influence of particle stiffness, or the Young's modulus of the particle. So generally what is done in the literature is, we try to do a sensitivity analysis. That means we try to lower the stiffness of the particles. As we try to lower the stiffness of the particle, the computation time step, the value of this time step increases. And as the time step increases, the computation time comes down. So we try to lower the stiffness of the particles to get a reasonable computation time. However, again, one has to be very careful as to what is the limit up till which we can reduce the stiffness of the particle while maintaining a reasonable accuracy of the results, at the same time reducing the computational load. Another technique which is used to reduce the computational effort or the computational load is called as coarse graining. So in this method of coarse graining, we try to increase the particle size by a particular scale factor. So what this does is it reduces the overall part count, and as a result, the computational load goes down. So with this brief introduction to discrete element method, let's switch to the DEM environment or the EDEM environment, and let's see how we can perform a discrete element method analysis. So this is the problem that we are going to be looking at. This is a very simple problem. So here you can see that there are two hoppers, or there are two silos. These two silos are geometrically identical except for the cone angle. Here you can see that the cone angle in this silo is 75 degrees, and in this case the cone angle is 15 degrees. And we wish to find out that what difference will it make in the granular flow, what difference will it make in the discharge of the bulk material. So now let's quickly jump over to the EDEM environment and let's see how we can model this problem. So this is the EDEM environment. As you can see here, this is the graphics area where we can see the model that we are working on. Up here we have the icon tray, and this is called as the creator tree. So this entire software, this EDEM software, is categorized into three segments. The first is called the creator, the second is called the simulator, and the third is called the analyst. So while setting up the model, we usually work from left to right in the icon tray and then from top to the bottom in the creator tree. So the first thing that I'm going to do is set up a working directory. So I'll go to File, Save As, and let's carry out all the simulations at this same working directory. So I'll just name it as Hopper High Cone Angle. So we have now set up the working directory. So the next thing that we are going to do is I'm at the moment in the creator tab, and I'm going to work from top to down, top to bottom in this creator tree. So the first thing that I'm going to do is I'm going to define that what is the bulk material and what are the properties of this bulk material. So to do that, I'll right click here and I'll say add bulk material. You can rename this bulk material, but at the moment I'm going to keep it as bulk material 1. So when you click on this bulk material, you can see that the software asks for what are the properties of this bulk material. So I have extracted a few properties from the literature survey. So let's enter those properties here. So these are some of the default properties that the simulation software is showing itself, but we are going to input our own user input properties. So for the Poisson's ratio, I'll enter a value of 0.3. For the solid density, I will enter a value of 4000 kilogram per meter cube. Then I'm going to use Young's modulus. In Young's modulus, I'll put in a value of 1 into 10 to the power 8 pascals. Also, you can change the units of this software. So to do that, you can go to Tools, then Options, and here you can see that you have units. You can set the units that you want. So there are several parameters and you can individually set the units of these parameters. At the moment, I'm going to leave these units as default. So now that we have defined the bulk material here, next thing that we want to do is we want to define the size of the particle and the shape of the particle. So to do that, we are going to click on this bulk material 1, right click, and we will say add particle. Now there are two options. We can add a polyhedral particle or we can make a multi-sphere particle. So in the polyhedral particle, we can model these particles in some CAD modeling software and import that particle shape here. We are going to be using this multi-sphere model, which is very easy and it is less time consuming. So now as we click on this multi-sphere model, we can see that there are several shapes that are there in the library. We can create our own custom shapes. So we can use a single sphere, that means the particle is of spherical size, that means the particle is of spherical shape. We can create some random shapes as well, or if the particle is of free-form shape or it is of non-spherical shape, then using these single particles or a combination of these single particles, we can create or we can approximate the particle size or the particle shape that we are working with. So for this example, we are going to restrict ourselves to one single sphere. So at this point, we are going to input the radius of the particle. So let's input a value of 15 mm. So this is the particle. This is one single particle. And we can calculate the properties simply by checking on this auto calculate button. You can click here. So the moment you click on this auto calculate button, all the particle properties have been calculated, and this is corresponding to the particle shape that you have defined and the bulk material properties that you defined earlier. So we can also define the particle size distribution. So for example, if you're working with a particle size distribution, that means in a given batch, you have some particles of a given size, then you have some particles of some other size, and these two are blended together. So you can specify that what is the ratio in which the two powder particle sizes are blended together, and then you can define the ratio of these two powder particles and work with them simultaneously. So at the moment, we have said that our particle radius is 15 mm, and this 15 mm powder particles constitutes the entire powder batch. The next thing that we are going to do is we are going to add an equipment material. Now I'm going to keep the equipment material same as the bulk material. So I'm going to enter the same properties as I entered before. So the Poisson's ratio was 0.3. Solid density is kept at 4000 kilograms per meter cube. And then the Young's modulus is 1 into 10 to the power 8 pascals. So having defined the bulk material and the equipment material, we need to define that what are the interaction properties. So to do that, I will come to this bulk material, I will click on the bulk material, and I will add an interaction. So to add an interaction, I'll simply click on this plus button. And now it says that what is the interaction property you're defining here. So between what two components we are defining these interaction properties? Are we defining this interaction properties between the two individual grains of the powder particles, or are we defining it between one powder particle and the equipment? So at the moment, I will set it to bulk material. So we are defining the interaction properties amongst the bulk material. And for that, we are going to assume that it has a coefficient of restitution of 0.6, a static friction value of 0.3, and we are going to have a high rolling resistance of 0.8. I'm going to again add another interaction between the bulk material and the equipment material, and I'm going to enter in the same interaction properties. So 0.6 for the coefficient of restitution, 0.3 for the static friction coefficient, and then 0.8 for the rolling resistance. So similarly, now I'll come to equipment material, and I'll go to equipment material and I'll add an interaction here. Here you can see that there is only one interaction possible, that is between the equipment material and the bulk material, which is already set. And I'm going to change these values again to the one that we mentioned earlier, 0.6 for the coefficient of restitution, 0.3 for the static friction coefficient, and then 0.8 for the coefficient of rolling friction. So now we have defined the bulk material and the equipment material. So the next thing that we need to define is the geometry. So in order to define the geometry, we need to model the geometry. I have already modeled the geometry in SolidWorks. Let me quickly show you the geometry. So this is the geometry that I have modeled. Here you can see that I have used surface commands only. You have the surface revolve, then surface fill, and then again surface fill. So I have modeled this as surfaces only because I don't want to import any unnecessary surfaces that can increase the computational load. So these are the only surfaces that are going to be interacting with the bulk material. So as you can see that this is the geometry here. The angle here is 75 degrees, and the opening is of radius 200 mm. I have also modeled this lid. So this lid is actually going to stop the bulk material from coming out immediately. It will allow this lid will allow this funnel to fill up, and then after we have given it sufficient time to fill up plus some more time to settle in, we are going to open this lid, and then we are going to be looking at the discharge of the granular material from this silo. We have also modeled a floor here. You can see that this is the floor. We also need to model a virtual surface. Now this is not a surface, rather it's a body. And the use of this virtual body is going to be clear when we import it into the DEM environment. So I am going to quickly section this and show it to you. So as you can see that this was originally my hopper, plus inside this hopper I have modeled this virtual body or this extrusion. So this is a simple body, this is a simple revolve that I have done. So this gives the simulation a location where it is going to place the particles. So having modeled these equipment material, what I'm going to do next is I'm going to save this as an STL file. We have looked at the STL file in detail in this course, so we are going to save this as an STL file. Now that we have saved this as an STL file, you can come to the desktop and you can see that this is the STL file that we have saved. So the next step is to import this STL file in the DEM environment. So to do that, I will come to geometries, right click, import geometry, and I will click on this STL file and I'll click open. Now it is asking me to set the import parameters. I'll set that my units are going to be in millimeters, and I'll set the size and bias to a value of 0.1. So this is going to prevent the mesh, the STL mesh, from distorting. So we will give it a few seconds so that it imports it in the DEM environment. Now you can see here that we have now imported this geometry in this DEM environment. So we can now rename these equipments. So this, as you can see, is the virtual body. So I'm calling this as the virtual body because this body is not going to take part in the simulation. It's not going to interact with the bulk material. It's not going to interact with any of the motions. It has no role to play in the simulation except to provide a location to input my particles, my powder particles. So I'm going to call it as virtual body. Virtual body. And again, I'm going to change this type from physical to virtual. This is the silo. To rename this, I'm simply pressing F2 on my keyboard and I'm going to name this as silo. Then this is the lid. I'm going to rename this to lid. And then this here is the floor. So next thing that I'm going to do is I'm going to import the particles or inject the particles in this virtual body. So to do that, we will right click on this virtual body and we are going to add factory. Now at the moment it is asking me, if we click on this new factory 1, this is asking me as to what is the generation rate. So that is how many particles or what is the total mass of the particle that needs to be generated for the given time period. At what rate do we want to generate the particles? What I want in this simulation is, I don't want the particle generation. Rather, I want to fill this entire virtual body with particles and then start the simulation. So that type of a particle injection comes under the static factory type. So to do that, to change this factory type, I can simply right click and I can click on this change factory type. Now you can see that the factory type has been changed to static, and I will click on this fill section. So this will ensure that during the start of the simulation, this entire virtual body is filled with particles, and then after, when it is filled with particles, the simulation starts. The next thing that I'm going to do is I'm going to add a motion to this lid. That means when the silo is filled with particles, this lid is going to open and the particles are going to discharge. So to do that, I need to add kinematics to this lid. So to add any kinematics to any particular geometry, I can right click, then I'll come to add motion, and then I'll add linear translation kinematic. So now you can see that it is asking me that what is the start time, at what time this kinematic starts, at what time this motion starts. So I'll start this at 1 second. So we will give some time for the particles to settle in. So after 1 second, the particles have settled in and the lid is going to open. Next, what we need to do is we need to define the direction of the motion. So to do that, to define the direction of the motion, we need to define an axis, we need to define a vector. So how to define the vector? The best way to define the vector is to consider that what is the center of mass of this particular equipment material, what is the center of mass of this lid. We can get the center of mass just by clicking here to mass. We will remove this auto calculate check mark and we are going to copy the XYZ location of the center of mass from here. So I'll copy this and I'll paste this here. Again, I'm going to go to the mass, copy the Y component, come back to my motion, place the Y component here, again go back to my mass, copy the Z component and place the Z component here. So that is the first point of the vector. We need to define the second point. So to define the second point, all I need to do is I need to change this either the X coordinate or the Z coordinate. So what I will do is I'll keep all the coordinates same. That means I'll keep the X coordinate same. I will keep the Y coordinate same. But instead of keeping the Z coordinate same, I'm going to change this Z coordinate value. I'm going to keep this at 0 mm. So now if I click on this display vector, you can see this display vector is going to take this lid from here and then it is going to translate this to this new location. We also need to define that what is the velocity of this translation. So we are going to define it as 0.8 meters per second. That is the speed with which this lid is going to open. So now we have defined all the geometric properties and the kinematic motions. Next we need to do is we need to go into the physics environment and we can set up our contact force models. Currently it is set to the Hertz-Mendelein no-slip theory and we are going to use a standard rolling friction model as well. But if you want to change this, we can click on edit change model and we can change, there are several contact force models, we can change the contact force models appropriately. Next we are going to go into the environment and here we will define the direction along which the gravity is acting. So at the moment it is set to negative 9.81 in the Z direction, which is incorrect. We want this in the Y direction. So I will copy this and I'll paste this here and I'll keep this component as 0. So now we have defined the gravity as well. So this is the pre-processing stage of the software. Now let's move on to the processing stage, that means the simulator tab. So I'll click on the simulator tab and now this is the simulation environment. So this is the simulator settings. We can change the simulator settings from this tree here. So now what we can do is, first I'll change this auto time step and I'll enter my own time step values. So to do that, I'll just simply uncheck this box and you can see that the criteria which is set here is the Rayleigh time step. At the moment it is fixed, so I'm going to change this time step to a value of 0001 seconds. So that comes around 19% of the Rayleigh time step value. Again, one has to perform multiple simulations in order to ensure that the time step is not causing any numerical instability, but at the same time it is giving accurate results. So I have taken this time step value from the literature. So the next thing that I'm going to do is, this is asking me to set the simulation time. So currently it is set to 1 second. I want the simulation to run for 60 seconds. So 1 complete minute. So I'll set it as 60 seconds. Next, it is asking me that at what interval do you want to save the data? If the save of the data is more frequent, then I'll have a bigger file size. If it is less frequent, then I'll have a lesser file size. So it is set, by default it is set to 0.01 seconds. I'll change this to 0.05 seconds. Then next is simulator grid. As you can see, this red box is showing the computational domain. This simulator grid discretizes this computational domain into number of small segments. This discretization is not it's not equivalent to the finite element or the CFT mesh that we usually see. This is different from those meshes. What we are trying to do here is we are trying to discretize this computational domain into number of small segments, and then we are going to mark only those segments that contains the powder particles to be active, and only active segments will be used for running the contact detection algorithm. So I'm going to set this cell size to 2.5 times of R. You can also click on this estimate cell size button, and it's going to show you that what is the optimum cell size depending upon what is the particle radii and then what are the motions that you have defined. So the next thing that I'm going to do is I'm going to select my simulator engine. Currently it is set to CPU solver, which is what I want, and the number of cores that I have assigned is 12 cores. I'll reduce it to 4 cores. So these are the simulator settings. Now what I'm going to do next is I'm going to click on this play button, and as soon as I click on this play button, the simulation will start to run. So I'll click on this play button, and you can see at the moment the simulation has not started because it is generating the powder particles inside the solid body, inside the virtual solid body we defined. So we will give it some time. And now you can see that the simulation is started to run. If we want to see the particles, we will simply click this button here, and we will also click this auto refresh button. And now you can see that the particles have been generated. Also, you can change the way these models look. Currently it is set to filled with an opacity of 1. I can reduce the opacity to make it more transparent, and you can see that these are the powder particles. This is the floor. Down here is the lid. I can also change this to points. That means only powder particles are visible, rest of it has been hidden. I can also change it to mesh, where it will show me the triangles of the STL file. You can see that these are the triangles of the STL file. And now we can allow this simulation to run, simulation to complete, and after the simulation completes, we'll come back again and we will post-process the results. Okay, so now you can see that the simulation is now complete. I had to reduce the simulation time down to 20 seconds because 60 seconds was way too much. So I reduced it to 20 seconds. And now the simulation is finished. All the powder particles that were inside the silo has now been discharged onto the floor. Next, we are going to move to the Analyst tab, and we are going to post-process these results. So for that, I'm going to click here. And now this is the Analyst Tree. So the first thing that I'm going to do is I'm going to step back to my first time step. In order to do that, I will click on this button here. And now you can see that the time is back to 0 seconds. If you want to slightly move the simulation forward, or if you want to move the simulation forward one step at a time, you can click on this button. You can click on this button, you can see that the simulation moves forward. If you want to run the simulation in a continuous manner, so for that you can click on this play button here. Because there are too many powder particles, you're not going to get a very good animation in this environment, but what we can do is you can export this to a video file, and there you can get a much better idea of what's going on. So as you can see that at 1 second, the lid opened and the powder particles are now starting to discharge from the silo. I can zoom in and you can see that the powder particles are now discharging from the silo. Again, I'll tell you how to export the videos. So at the moment I'm going to stop this animation, otherwise it's going to take some time. and we are going to explore a few other options in the analyst tree. So again, I'm going to move to the first frame or the first time step, and I'm going to move a few time steps forward till the particles appear. So here I have all the particles. Let me change this view to a view which is perpendicular to the z-axis. Now what I want to analyze is how these powder particles discharge when the lid is opened. So to do that, I'm going to color different sections of this silo, the particles in various sections of this silo. So for that, what I need to do is, I need to create a setup selection. So to create a setup selection, I will come to setup selection, right click, I'm going to add a selection, then I'm going to click on manual selection. After clicking on the manual selection, I will enable the manual selection checkbox here. Now when you come to this viewer window, I can select a certain number of particles and give them a certain color. So I will select these particles, then I'll go to display, then I'm going to go to selections, particle selections, and then manual selection. I'm going to check mark this box which says color by selection group. Then at the moment it is set to uniform, I'm going to change the color to let's say green. Next, I'm going to create another selection, another setup selection. So I'm going to come to setup selection, right click, manual selection, enable manual selection. Then I'll come to this viewer window and I'll select a particular segment. So let's say this much I'll select. Come back to this manual selection too, and I will check this box and assign a color of let's say yellow. Again, I'm going to come here, add a manual selection, enable the manual selection, and then I'm going to come here, set up a set of particles, select a set of particles, come to this manual selection, check this color box, and let's say that these are orange. And let's do one more where I will right click, manual selection, enable manual selection, select these particles on the top, come to this manual selection 4, color selection, color by selection group, and this time let's do a pink particle here. Okay, so now I have discretized, or I have created these bands of bulk material, and now what we wish to see is how these bands of bulk material are going to discharge when the lid is opened. So again, now if we can click on this play button, and we can see the discharge of these powder particles. So this is the time where the powder particles have settled in. So at 1 second the lid opens and you can see the discharge. You can clearly notice here that the green particles discharges first, followed by yellow, which will then be followed by orange, and then finally the pink particles will discharge. Again, what we can do is, to speed up this process, we can create a video file where it's going to render on all the frames and play it in a one continuous smooth fashion. And you can see how this powder pile is getting created on the floor. You can use the right click to rotate the model, and then you can use the left click to pan the model, and you can use the scroll wheel to zoom the model. Now you can see that the yellow particles are being discharged, which will then be followed by orange powder particles, and then finally the pink ones will be discharged. So I'm going to stop here, and I'm going to show you a few other options. Suppose I want to measure some of the attributes of these grains, or these attributes of this bulk material. So for that, we can create another setup. Suppose I want to measure that what is the mass flow rate. To do that, we can come to this setup selection, right click, and we can select this add sensor selection, and we are going to add a mass flow sensor here. Now you can see that the mass flow sensor is showing the discharge of the powder particles in UK tons per hour. We can change the units. I'll go to tools, change the units. We can change it to some other values. Let's say we want to keep kilograms per hour. You can click here. Next, what we are going to do is, you can see that this sensor, I want to place this sensor right at the outlet. But at the moment, it has its own position. We can change its position by appropriately adjusting its coordinates. So how to adjust its coordinates such that this sensor aligns with this outlet, the outlet of this silo? Well, we already know that what is the center of mass of this silo. If you don't remember it, what you can do is you can come back to this analyst tree. You can go to this funnel, open this menu, go to the mass, and here you can see the center of mass here. I can uncheck this box and I can copy these values to, let's say, a notepad. So I'm going to copy these values. Let's see, I'm going to paste it here, paste it here. See, I'm going to paste it here. Now I'll recheck this box and I'll come to the Analyst tab. Now I know the center of mass of this funnel. So one of the start points could be the center of this mass. So I'll simply copy and paste these values in this start point. So that's the X component, this is the Y component, and then this is the Z component. So that's the first point. The second point could also be the same, but with a slight variation in the Y. So I'll come here, paste it here, and then I can click on apply. So now you can see that the axis of the sensor is now in line with the axis of the funnel or the silo. We can appropriately adjust this Y values so that we get this sensor right at the outlet. I did this before, and I found that if you enter the value of 1600, the coordinate values of 1600 versus 1400 mm here, you will place this sensor right at the outlet. Again, this takes some trial and error, but it is very easy to do. The radius at the moment is set at 1000 mm. I can change this value to, let's say, 500 mm, and again click on apply. So now that we have created this sensor, what we can do is we can go to its graphing calculator. So here you can see that this is the option to create graphs. So I'll come here, and there are several options within this graphing calculator. I can create a histogram, I can create a line graph, I can create a scatter and a pie chart. So I want to create a line graph. So I'm going to click on this tab. Then in the selection, I will change this to mass flow sensor 1. X-axis is going to give me the time range, and in the Y-axis, I can set different attributes. So at the moment it is set to angular velocity. I can have different attributes, I can measure different attributes. Let's say I want to measure the number of particles. So I'll simply click here, and I can click on this create graph. We'll give it a few seconds because there are lots of particles here. So it's going to take some time to generate the graph. Okay, so now you can see that this graph has been generated where it shows number of particles on the Y-axis and time on the X-axis. Similarly, there are lots of attributes and you can explore these attributes on your own. One other thing that I would like to show you, that if you want to export these results for further processing, you can simply right click and you can click on export as text. I'm going to click on desktop, and we can give an appropriate file name, data, which is corresponding to the high cone angle. Click on save, and you can see that when we come to the desktop, there is the Excel file which we can use for further processing. These are the time steps, and then over here are the number of particles. So that is how one can simulate in DEM software. So this is all about the simulation when the hopper angle was too high. What happens if the hopper angle is too low? As was the case I showed you in my PowerPoint, where the hopper angle was only 15 degrees. So I have already performed that simulation, and I'll quickly like to show you the results. So we can go to open simulations. We'll open this simulation here. It's going to start loading the files. Okay, so now the files have been loaded here, and you can see that I have kept every parameter the same. You can look in the bulk materials. You can look in the equipment materials as well. I have kept the particle size the same of 15 mm. The outlet is same as 400 mm. That is, the dia of the outlet is 400 mm. Everything is the same. This is the lid. I have added the motion to the lid as well, kept it at 0.8 meters per second. So every parameter is the same. The only change is in the cone angle. So again, if you want to analyze this, we can come to the analyst tree. We can go to this graphics viewer, and now you can see I will just step to the first time frame, a few time frames following that, and these are the segments that I have already created. And again, I have added this mass flow sensor here. So every parameter is the same. The geometric parameter, the material parameter, and the interaction parameters, all these three parameters are the same. Now I want to show you how you can export this, export the video. So if you want to export the video, what you can do is you can come down here to the scheduler, and you can click on this record animations tab, record animations button. You can click on this. You can set the locations where you want to export the video to. I'm going to export it to my desktop, and let's call it as low cone angle. Low cone angle. Click on save. I'm going to export an MP4 videos. However, you can export the videos in other formats as well. Rest of the settings you can keep as default, and you can click on OK. Now you can see that this record button is armed, and all you need to do is simply play the simulation. So when you play the simulation, it's going to take some time, and as it plays the simulation, it will export the video. So you want to wait till the entire simulation is finished in the DEM environment, and then you can open the simulation file, open the video file with some any video player that you have. Okay, during export, if you make any changes to this model, so for example, if you rotate this, then the exported video file will have this rotated view. Another thing that you can do is you can create a cross section of the part and look at the cross section of the part to get a better understanding of what the bulk matter behavior is. These are called as clippings in the DEM environment. To create a clipping, you simply come to this clippings tab and check this box, which is called as clipping. We want to add a clipping plane, so I will click on this drop down menu, and I'll click on clipping plane. You can see that I can orient this clipping plane. At the moment it is set to 1, x-axis is set to 1. That means the clipping is perpendicular to the x-axis. Now what you can do is, you can just uncheck this view representation box, and now what you can do is, when you run the simulation, you will see the clipped view. That means this is now the cross-section view. And now you can see how the particle is going to discharge from the cross-sectional view. Again, you can export this video. If you view the video in the DEM environment, because lots of particles are being rendered, it's going to take some time, so it's better to export this as a video and then view your results in a video player. So I have already compiled all these results in a PowerPoint slide. Let's switch to the PowerPoint and analyze some of these results. So now we are here in the PowerPoint, my presentation. You remember that these were the two cases we were trying to study. One was that of mass flow, other was that of funnel flow. So what difference does this cone angle make on the granular flow behavior? You can see for the case of mass flow, that means with very high cone angle, the particle discharges in a layer-wise fashion. If you remember, the green particle was the first layer, closest to the outlet, followed by the yellow layer, then the orange layer, then the pink layer. And you can look at the flow pattern or the pattern in which the discharge has taken place. You can see that the green layer has discharged first, followed by the yellow, followed by orange, then by pink. So with a very high cone angle, the discharge takes place in a layer-wise fashion. However, in the case where the cone angle was very low, that is the case of funnel flow, you can see that for the first few time steps, the discharge was layer-wise. So the green particles have discharged first, but progressively the degree of mixing has increased. The particles amongst these layers have mixed. And what is also surprising is that the pink layer which was the topmost layer in the segments that we created, is buried inside this pile. So this is a very peculiar observation that one can make. Again, from these images, you can see that for the case of the mass flow, there is a layer-wise discharge, but for the case of funnel flow, there is a layer-wise discharge for the first few seconds, for the first few time steps, but then later on, the discharge becomes more erratic and the degree of mixing is quite high. Another thing that you can notice here is, if you plot the number of particles discharged versus the time step, you can see that in funnel flow, the discharge rate is quite low. Whereas in the case of mass flow, that means a cone angle of very high value, the discharge rate is very high. So the powder particles have discharged much more quickly in the case of mass flow as compared to the funnel flow. So let's look at the animation. So this is the animation showing the mass flow and the funnel flow. You can see that the green particle has discharged first, followed by the yellow particles in the case of mass flow, followed by the orange particles, and then finally we have the pink particles here. Whereas in this case, you can notice that the green particles initially discharged first, but then it's the pink particles which discharged, followed by the rest of the color of the particles. And you can see the difference that it makes in the discharged powder piles. Again, I want to show you that this is the case where the pink particle is going to discharge first, then all the orange particles are going to discharge, followed by some of the yellow ones and then the pink ones. One other phenomena that you can observe is the phenomena of rat holing. That means the pink particle has a higher velocity, has a higher discharge velocity as compared to the other powder particles. As you can see, the pink particles discharges first, and then you have very small velocities of the yellow particles here. You can also monitor these phenomena in a much more quantitative way, where you can calculate the discharge velocities of each of these individual selections in the DEM environment. So another phenomena which is quite interesting and is in the context of additive manufacturing is in the case of recoating systems for powder bed-based additive manufacturing. We already know that for the case of rollers, when rollers are used for spreading the powder onto the print bed from the reservoir, there could be two possibilities. First, the roller can assume a counter-rotating orientation, counter-rotating configuration, or it can assume a forward-rotating configuration. So here are the two configurations. This one is the counter-rotating configuration. The roller rotates opposite to the direction of travel. And this is the forward-rotating configuration, where the roller rotates towards the direction of travel. Now let's see what discrete element method simulations can reveal for both these two categories of recoating system for powder bed-based additive manufacturing. So I have already modeled this problem in the DEM environment. I will quickly show you the relevant details. So let's go to the DEM environment. And here you can see that this is my model. This is the roller. This red color part is the roller. It can either assume a forward rotating or a counter rotating configuration. The rest of the parameters, be it material, geometric, or interaction properties, all these parameters are going to remain the same. The only difference is that one configuration would be for the forward rotating variety and the other configuration would be for the counter rotating variety. Here you can see that this part, which is highlighted here, this part is going to be the powder reservoir. So this is going to contain the powder particles, which is then going to be spreaded onto the powder bed. So this is going to be the powder bed or the print bed. So this portion, which is dark red, this dark red portion is going to be the print bed. Currently, the way I have modeled this problem is it's going to support a layer thickness of 75 microns. So that's the geometric modeling part. I have also modeled two side walls, as you can see here. These two side walls are going to prevent the powder from falling off during the recoating cycle. So this is my bulk material properties, as you can see. So these properties are very close to what you will see in the case of ceramic powder particles. However, I have dramatically reduced the Young's modulus to reduce the computational load, of course. This is the powder particle size. You can see that it's around 25 microns. So now let's look at the equipment material. So these are the property of equipment materials, and then these are the interaction parameters. I have again used these interaction parameters from the literature survey, and I will provide a reference to the paper towards the end of my presentation. So I have already discussed the geometries that are going to be involved in this simulation. Now let's look at the motions. So the motion or the kinematics is only assigned to this roller. The rest of the geometries which are part of this DEM model are stationary, are static. So what are the motions that are associated with this roller? First, it's going to rotate about its own axis, and second, it's going to translate about a given axis. So let's look at these two motions. So this is the first motion, which is the rotation. Currently, the rotation is set at 240 RPM. And if I were to click on this display vector, you can see this is of counter-rotating variety. That means the direction of travel is towards positive x, and it is rotating against the direction of travel. So this is the linear travel of this roller. Again, if I click on this display vector, you can see that this travels from this end to this end. So this is the vector which points to the direction of its travel. The travel speed or the travel velocity is set to 0.02 meters per second. So these are the two kinematics, two motions associated with this roller. Now let's look at the physics. This time, I'm not using Hertz-Mendelin, the simple Hertz-Mendelin model. Rather, I'm using Hertz-Mendelin with JKR. The only point, the difference between these two models from the user input side is that for the case of Hertz-Mendelin with JKR model, if I were to click on this gear icon, you can see that an extra input that is required from the user side is that of interfacial surface energy. As I previously mentioned, that Hertz-Mendelin with JKR model is used for the simulation of cohesive media. That means the powder particles, they have a force which is trying to push them together. That's the cohesive nature of the media. So apart from the rebounding force which they experience upon contact and the damping force which mimics the loss of energy during contact, there is an additional force which is called as the cohesive force, which tries to push these two particles together. So that cohesive force is modeled using JKR model. So I have put in a value of interfacial surface energy as 0.0015 joule per meter square. So with this setup, I will now move to the simulator tab. And again, you can see that what are the parameters I'm using here. Here currently, I'm using a time step of about 5 into 10 to the power negative 8 seconds, so which equates to 20% of the Rayleigh time step. The total time of the simulation is set to 2 seconds. The save interval time is 0.01 seconds. The grid size or the cell size is 5 times of the particle radius. And I have assigned a total of 4 solvers, CPU solvers, to run the simulation. So that is the settings for the simulator. So now we are going to run the simulation. You can see the moment I click on this play button or I start the simulation, this part of the platform, which is supposed to be the reservoir which contains the powder, and the roller is going to pick this powder and spray it onto the and spread it onto the print bed, is now filled with powder particles, and the roller will start moving. This roller is going to start moving at a designated time in the simulation. So I have already performed this simulation. So I'm going to stop this simulation and I will load the completed files. Okay, so now these are the complete simulation files. I have made a few changes here. Let me walk you through these changes. So the first change that I have done, so the first thing that I'm going to do is I'm going to move it back to the first time step. So this was the first time step. Let me orient it in a way which is easier to understand. So this is the first time step. And after I step through a few iterations, you will see that the particles have now appeared. Again, I have now layered these powder particles and I have colored each of these individual segments just to give an idea as to how these powder particle or how this powder pile is transferred from the reservoir bed onto the print bed. Also, because this roller was an STL file and there were lots of triangles here, if this were to rotate, its rotation was not very clear that whether it is rotating or not. So what I did was, so I went to this display section, went to geometries, I selected this, so this is my roller. You can see that if I uncheck this, this disappears. So I'm going to check it back again. So this is my roller, and instead of having smooth colors on it, I went ahead and I said that this has to be colored by the triangle ID. And I assigned 3 colors to this so that I can get a nice gradient, and when this roller rotates, we can see its rotation, we can monitor its rotation. So again, in terms of coloring these particles, I went ahead and created these manual selections, and each of these selections were assigned the color. I have already discussed this previously. I also imported a geometry bin group. So if you want to see this, you can come to this display mode and turn this to always. And so now this is my measurement bin. You can see that this bin is highlighted by this green color outline. Again, this is a rectangular measurement bin, and we are going to be looking at the attributes of these particles within this bin. So whatever is happening on the print bed, that is the part that we are interested in, and that is captured by this green colored bin. So what are the different attributes, or what are the different properties of these powder particles we can look at that can suggest the difference, or that can highlight the difference between these two variety of rollers, counter rotating and forward rotating rollers? So I have decided to select 2 properties. The first property is that what is the compressive force on these particles. Compressive force, by compressive force I mean what is the compressive force which is exerted by the rollers on the print bed. So that is easy enough to plot. So what you do is you just come to this graphing calculator here. I will come to this line plots. I'll select particle only. Then in this selection, I will select imported bin group 1, because this imported bin group 1 captures what is happening on the print bed. Its domains or its boundary is oriented such that it captures everything that is happening on the print bed. So I will select this. On the x-axis, I want the time steps, and in the y-axis, I have several attributes to choose from, but I'm going to select this compressive force. Instead of average, I'm going to be looking at total compressive force, and then I'm going to click on create graph. So we'll give it a few seconds so that it creates the graph. Okay, so this is the compressive force graph that it has generated. You can see that for the first few time steps, there is no compressive force on the print bed, or there is no compressive force in this bin. The reason is there are no particles in this bin. During these time steps, all the powder particles are on the reservoir side of the platform. But so after a few time steps, you will see that the powder particles from the reservoir are transferred onto the print bed, and the roller starts to move over it. So this is the case of backward rotating or counter rotating roller. So I'm going to export this in a CSV file so that I can further post-process these results and perhaps do a comparative study. Let's give this a name. Let's call it counter rotating, and we can click on, let's save on desktop, and we can click on save. Another parameter that we are going to look at is a parameter which is called as void edge, and I'll formally define what this parameter is. But for time being, let's just create a graph for void edge. So I'll go and I'll click on this void edge, and then I'm going to create a graph for that as well. Okay, I'm going to export this graph also. I'm going to export this to my desktop. So these are the 2 primary attributes that I think are going to highlight the difference between a forward and a counter rotating ruler. Let's also look at the simulation results in the form of animation that this software has provided us. So we can either export this video, but because in this case the number of particles are significantly lower, so I feel that the animation in this environment will be able to provide us with a fairly smooth render. So to play the simulation, I simply click on the play button. and you can see that this is a counter rotating roller. It takes the powder from the print bed and moves it onto the reservoir and moves it onto the print bed. You can also notice that some of the particles are sticking to the bottom of this print bed because of the cohesiveness of these powder particles with the equipment material. Okay, so that is about the counter rotating roller. Let's also quickly look at the forward rotating roller. So I have already performed the simulation. Let me load up the simulation files. Okay, so now this is the case for the forward rotating roller. I have loaded this in the DEM software, and I want to show you that all the properties are kept same. The bulk material properties, the equipment material properties, and the interaction properties are all kept same. However, we have changed the motion that is associated with this roller. So if you look at the rotation, if I were to click on the rotation axis, you can see that this is the rotation axis. That means it is moving clockwise. Also, if you were to see the travel direction, so I will go to this new motion 2, click on this display vector, and then this is the travel direction. So this rotates towards this travel direction. So it is rotating in the travel direction. Rest of the parameters remains the same. If you were to go to the physics, click on the gear icon, you can see that the interfacial surface energy has not changed and rest of the parameters are constant. So again, you can see that the time step is kept at 5 into 10 to the power 8 seconds, which is around 20% of the Rayleigh time step. The grid size is kept at 5 times r, 5 times the particle's radius. And there were 4 CPU solvers to solve this problem. Now let's move to the Analyst tab. So this is the simulation results. Let me quickly go back to the front of the simulation and move forward a few time steps. And you can see that this is the simulation for the forward rotating roller. So let's look at the animation which is given by this software. So to do that, I'm going to simply click on this play button. And now you can see that the rotation is now in forward rotating configuration. You can see that the roller rotates and it takes the powder from the reservoir and spreads it onto the print bed. So the next thing that I'm going to do is, for the case of forward rotating rollers as well, I'm going to export what is the compressive force and what is the void edge, and then I'll compile these two results and show you a comparative analysis. So okay, so now I have compiled my results in this section of the PowerPoint. Let's quickly look at it. So in this animation, you can see that this is the counter rotating roller. It takes the powder from the reservoir, spreads it onto the print bed. And followed by this, you will see the case of the forward rotating roller. So now this is the case for the forward rotating roller. So now you can see here that as far as the compressive force on the powder particles on the print bed are concerned, you can see the graphs here. The blue color represents the compressive force on the powder particles when it is of forward rotating variety, whereas red curve represents the compressive force when it is of counter rotating variety. You can see that at time step which is equal to 0.75 seconds, somewhere around 0.75 seconds, the print bed starts to receive the powder particle. In fact, it is quite clear from this animation also that initially there is no powder particles onto the print bed, but the roller at around 0.75 seconds, the roller comes onto the print bed. And as soon as the roller comes onto the print bed, it starts to exert some compressive force on the powder particles below. So again, you can see from here that at 0.75 seconds, the roller came onto the print bed. And as soon as it came onto the print bed, it started to apply some compressive force, some downward compressive force onto the powder bed below. And you can see that for the case of forward rotating roller, the values of the compressive force is significantly higher as compared to the values of compressive force when it is of counter rotating variety. Let's now look at the other attribute, which is called as the void edge. Now void edge, as the name suggests, has something to do with how much of the volume is occupied by the powder particles and how much of it is left empty. In other words, if we were to look at the bin that we defined, which was defined by the green outline as I mentioned in the DEM environment. So if we were to look at that bin, and we were to calculate what the volume of the bin is versus what is the volume which is occupied by the powder particles which are inside the bin. And if we were to subtract these two values and divide it by the volume of the bin, we will get this parameter which is called as voidage in terms of percentage of cost. So it is the volume of the bin, that means the total volume which is occupied by the bin, minus the volume which is occupied by the powder particles divided by the volume of the bin. So if the voidage is high, that means that the volume of particles which are within that bin, within that specified bin, is low. Or conversely, if this voidage is low, that means that more particles are there in this particular bin, which will indirectly signify a higher compaction. So now, as you can see from this graph, that this red color curve gives us the voidage when we use a counter rotating configuration. So in this configuration, you can see that the value of voidage is quite high, which signifies that within that bin, the volume that is occupied by the powder particles is quite low. Conversely, if you look at the forward rotating roller, then the value of voidage is quite low, which implies that there is very high compaction. That means there are higher number of powder particles within that measurement bin as compared to the counter rotating rollers. Indirectly, which means that the compaction for the case of forward rotating rollers is quite high. One other way in which you can interpret this result is that for the case of counter rotating rollers, most of the powder particles were pushed off from the print bed. Instead of being compacted on the print bed, these powder particles were pushed off from the print bed, which can indirectly signify a higher flowability that is achieved for the counter rotating case. For the case of forward rotating case, because the voidage is quite low, most of these powder particles were compacted onto the print bed, thus signifying poor flowability. And these results are in agreement with what we have seen in the literature. So with this, I conclude this session. So these are some of the references I have used. Thank you very much for your kind attention.